Hello and welcome to another video presentation courtesy of the University of North Texas Physics Department with the assistance of the Physics Demo Room. My name is Corey Nook and I'll be talking about a concept today dealing with rotational motion and torque. So the first thing we have to talk about with rotational motion is this concept of angular acceleration. And angular acceleration is just the rate at which the angular velocity is changing with respect to time. Now, as we might have talked about before with uniform circular motion, but that was assuming that your angular acceleration was always zero. Well, now we're saying, well, what if the angular acceleration was non-zero? That way, the actual angular frequency, or how many revolutions per second, actually changes. So with that, we have to talk a little bit about how angular acceleration is related to torque. So torque, by definition, on the board that you have behind me, is that tau, which stands for torque, is equal to the radius from which you are from the pivot point times the force applied times the sine of the angle theta. Now theta is with respect to the zero axis and between the radius direction and the force applied. So if we are looking at a zero direction, and we're now going counterclockwise, that is a positive torque. But if now we're going in the other direction where we're actually going clockwise, that would be a negative torque. The reason why that a counterclockwise applies a positive direction is we think about the unit circle. We measure 0 degrees from the positive x-axis and going up towards noon or going to the positive y-axis, that is a positive angle, which is a counterclockwise direction. So if we went in a clockwise direction, that is a negative angle. This is why you have to be a little bit careful about counterclockwise and clockwise with the associated positive and negative directions. Well, we have defined torque now in terms of a radius and a force. But torque can also be defined similar using Newton's second law of circular motion, which is that the sum of all torques on an object equals its moment of inertia times the net angular acceleration, which I have written below. That tau is equal to the moment of inertia I times alpha. Yes, these are Greek letters. Do not confuse them with A or T. There is a purpose to why we have them labeled as we do. So now if we were to look at a situation to where, well, what if I was to change my two objects and see how they relate to each other? Well, I can have that the angular acceleration is related in terms of the torque over the moment of inertia. So to illustrate what I'm trying to talk about here with this different angular accelerations is ideally this piece would be exactly half of a meter stick. I don't exactly have that on hand. So I have a thin ruler and I have a meter stick. So I'm going to put these two side by side. Actually, I'm going to let you hear first what they sound like when they hit the table. So now what I'm going to do is I'm going to put these two rulers side by side and I'm going to create a pivot, or I'm going to create a pivot point for these two to just fall and hit the ground. And I want you to see if you can see a difference between when they hit the ground. It looks like the smaller object hit the ground first, then the larger object. This has to do with that the radius, or where the center of mass of this object, that if we were to put this as a point mass, is closer to the radial point than the longer meter stick, which means that allowed it to actually have a higher angular acceleration. Now you might be saying, well, how do we calculate this angular acceleration? Well, if we think about it, this object is just any other object that we have on Earth. That the force being applied is really its mass times the acceleration due to gravity. But when I actually have it at an angle above here, the angle is not perfectly at a 90-degree angle compared to R. My force is actually going straight down from here, which creates an angle of above 90 degrees, which means that we're going to have some component that's not just going to be R times F. If it was perfectly going to be just R times F, I would have R going this way and F going up here. Just like I'm trying to make a turn signal if I was a bicyclist. Or a cyclist, depending on how you would like to be called. So with these two cases, this center of mass, if this is perfectly uniform, is about halfway. It's about 50 centimeters. Whereas this is about, this is about 50 centimeters total. So it's going to be about 25. So the radial distance away is about half. Now you will notice that this is a lot thinner than the other object, but hopefully the overall mass difference is not substantially different. Now I will show later on about the actual calculation that if we did have a perfect difference, what is going to be the change in the acceleration between these two objects in terms of this was 1 meter and this was exactly half the mass and half the length. So this would be 1/2 of the mass of our 1 meter ruler with a total length of 50 centimeters instead of 100. Well, so now that we talked about that this one, because it has the shorter lever arm, is going to have a higher angular acceleration, we're now going to go into a demonstration called the falling chimney. This is also the reason why whenever a chimney is fallen, let's say a big long building, you might see that the bottom end kind of comes out first and then the top. Well, it's the same concept kind of with this, is that I have this steel ball in my hand, and I have this meter stick that's attached down at the base here. And so what I'm going to do is I'm going to raise this up to a certain height, I'm going to hold on to it, and I'm going to let go. And when I let go, this angular acceleration of the meter stick is going to be faster than the ball is going to be able to stay on the meter stick. So its inertia is going to allow it to fly off the meter stick or not keep up with the meter stick, and it's just going to fall straight down the ground because it's in free fall. Whereas the meter stick is going to have an angular acceleration. It will accelerate upwards to where when I release this, this ball is going to land in this kind of little cup that you see here on the bottom right there. So let's see if I can get this right. Now it might take me a try or two to get it completely right, but hopefully I was really close. It was just a little bit off in terms of it didn't want to stay there. We'll see if I can do this one more time. Nope, that one didn't work. Last time. Good luck charm. There it is. As you can see, the ball has stayed inside the little cup because of the angular acceleration was greater for the meter stick than it was for the ball because of the center of mass of the ruler being closer to the pivot point. Again, I am going to go over a little bit, as you kind of see on the writing over here on the board, about the two meter sticks if we had the different lengths and the mass ratio. Well, I hope that you appreciate this little demonstration today, and you have a wonderful day. So this is a continuation of the falling chimney demonstration. So I really wanted to go through the mathematics of why the torque, if we were able to have a meter stick that was half the length along with half the mass, would have a higher angular acceleration than the longer one. So let's just say with our initial meter stick that we have, that it has some radius away from our pivot point, we call that R0, and that the force acting on it is just some initial mass times gravity times the sine of the angle. But now if we had a second meter stick that we were going to say now the total length of it, or the center of mass, is now half of what the original center of the original meter stick is, and that the total mass of our second meter stick is half the mass. So this would, instead of saying, well, if our initial radius was a 1 meter length meter stick, and the initial radius would be only 50 centimeters, because that's the center of mass, then if we had a meter stick that was only 50 centimeters, its new center of mass would be 25. And the same thing is that if we had a meter stick from 1 meter down to 50, that's taking half the mass away, so our half meter stick should have half the mass of the initial object. So now if I was to actually put this as the torque and calculate this, and I put in that I would have 1/2 and 1/2 into my top equation there, 1/2 times 1/2
gives me that the second torque is 1/4 of my initial radius and our initial mass. So the torque is really going to be equal to 1/4 of the initial torque. But now we look at the moment of inertia, because the moment of inertia is related to both the mass and the radius. So the moment of inertia is defined as mr squared when you're pivoting about the endpoint. There might be another factor out here, but that factor will in essence go away with here. So now if we look at our second meter stick, and we say that this is our initial moment of inertia, our second meter stick has half the mass, but it also has 1/2 of the radius. But when I square that 1/2, it becomes a 1/4. So now that actually becomes 1/8 m naught v naught. M naught r, not v, r, which is equal to I2. So now if I was to solve that alpha is equal to, or alpha 2 is equal to tau 2 over I2. If I was to resolve this in terms of our known values, which is 1/4 tau naught and 1/8 of I naught, because m naught r naught squared is just I naught, then I'm going to get that alpha 2 is really 1/4 over 1/8 of tau naught over I naught, and 1/4 divided by 1/8 is really 2 alpha naught. So I hope that this kind of alludes that now that if we have a meter stick with half the mass and half the length of the original meter stick, the angular acceleration will be twice of that of the original meter stick. Well, thank you for listening to this little additional spot about the mathematics with it, and have a wonderful day.